Every single day, this factory turns ordinary sand into something extraordinary. Solar panels capable of powering entire cities. The journey from sand to clean electricity takes 14 days, 400 steps, and temperatures hotter than lava. It starts here, with silicon heated to over 2,500 degrees, until it flows like water. China produces more than 80% of the world's solar panels, factories stretching across landscapes like small cities. Automation and human expertise work in perfect rhythm, producing enough panels every hour to cover 2 football fields. Global solar capacity has grown 100-fold in 2 decades, and factories like this one are the reason why. Each panel contains 60 to 72 cells, every one cut from a single crystal of pure silicon. But first, we start at the beginning, with sand pulled straight from the earth. Before the transformation can begin, engineers test every batch of incoming silicon, verifying crystal structure and electrical properties meet exacting specifications. The solar supply chain spans the globe. Raw quartz mined on one continent is refined on another and assembled into panels on a third. Container ships carry thousands of tons of silicon materials between continents, feeding factories that run 24 hours a day, 7 days a week. Every kilogram of raw material is tracked from mine to factory floor. Digital traceability, ensuring quality at every link in the chain. Before the transformation can begin, engineers test every batch of incoming silicon, verifying crystal structure and electrical properties meet specifications. The solar supply chain spans the globe. Raw quartz, mined on one continent, is refined on another and assembled into panels on a third. Container ships carry thousands of tons of silicon materials between continents, feeding factories that never stop running. Every kilogram is tracked from mine to factory floor. Digital traceability, ensuring quality at every link in the chain. The raw material for every solar panel is silica sand, one of the most abundant minerals on the planet. But not just any sand will do. Solar-grade silicon requires quartz with a purity above 99.5%. After mining, quartz is crushed and screened, removing impurities before the first chemical transformation begins. The purest quartz on Earth comes from Spruce Pine, North Carolina, a small town that quietly supplies the entire global semiconductor and solar industry. High-pressure washing removes clay and organic contaminants. The quartz must be spotlessly clean before entering the furnace. The difference is visible to the naked eye. From muddy brown rock to crystalline white quartz, ready for smelting, conveyor belts feed a continuous stream of crushed quartz into the smelting facility. This plant alone consumes 50,000 tons of quartz every year. X-ray fluorescence analyzers verify purity on the spot, rejecting any batch that falls below 99.5% silicon dioxide. High-pressure washing removes clay and organic contaminants. The quartz must be spotlessly clean before entering the furnace. The difference is visible to the naked eye, from muddy brown rock to crystalline white quartz ready for smelting. Conveyor belts feed a continuous stream of crushed quartz into the smelting facility. This plant alone consumes 50,000 tons every year. X-ray fluorescence analyzers verify purity on the spot, rejecting any batch that falls below the minimum threshold. Inside the arc furnace, crushed quartz meets carbon at 2,000 degrees, stripping away oxygen to leave metallurgical-grade silicon. Molten silicon pours like liquid metal, already 98% pure, but nowhere near clean enough for solar cells. Metallurgical silicon is worth $2 per kilogram, but after purification, that value increases 50-fold. From the smelting plant, metallurgical-grade silicon ships to dedicated purification facilities, often in a different country entirely. At the purification plant, every incoming shipment faces chemical analysis, even trace contaminants in parts. Per million must be identified before processing begins. From the smelting plant, metallurgical-grade silicon ships to dedicated purification facilities, often on a different continent. At the purification plant, every shipment faces chemical analysis, trace contaminants in parts. Per million must be identified before processing. The Siemens process is where the magic happens, converting metallurgical silicon into polysilicon with a purity of 9 nines. Each reactor runs for 7 days straight, slowly depositing ultra-pure silicon onto thin seed rods inside the chamber. What emerges is polysilicon, the purest material humans can manufacture, with impurities measured in parts per billion. These rods are broken into fist-sized chunks, each worth its weight in silver. Solar-grade polysilicon sells for roughly $20 per kilogram, a 10-fold markup from the metallurgical-grade material it started as. Resistivity testing confirms purity levels. Each batch must reach 9 nines, meaning 99.9999999% pure silicon. Graded polysilicon chunks are stored in climate-controlled warehouses, ready to feed the crystal growing furnaces next door. Loading the crucible is an art. The arrangement of chunks affects how evenly the silicon melts and the quality of the final crystal. Resistivity testing confirms purity levels. Each batch must reach 9 nines before moving to crystal growth. Graded polysilicon chunks are stored in climate-controlled warehouses, ready to feed the crystal growing furnaces next door. Loading the crucible is an art. The arrangement of chunks affects how evenly the silicon melts and the quality of the crystal. Now comes one of the most remarkable steps in manufacturing, growing a single crystal of silicon from a pool of molten polysilicon. A seed crystal touches the melt and begins to rotate, pulling upward at just 2 millimeters per minute, while a perfect crystal forms behind it. Over 36 hours, a single ingot grows to nearly 2 meters tall, weighing over 200 kilograms of perfectly aligned silicon atoms. Diamond wire thinner than a human hair slices the ingot into wafers 150 micrometers thick, thinner than 2 sheets of paper. A single ingot yields over 5,000 wafers, each one destined to become the heart of a solar cell. The wire saw room runs around the clock, each machine slicing an entire ingot in under 4 hours while maintaining micrometer precision. The diamond wire is just 120 micrometers in diameter, roughly the width of a human hair, yet strong enough to slice through solid crystal. Edge-rounding chamfers, each wafer's sharp corners preventing microchips that would propagate into fatal cracks during cell processing. Laser scanning maps thickness variation across every wafer. Any spot deviating more than 10 micrometers triggers automatic rejection. The wire saw room runs around the clock, each machine slicing an entire ingot in under 4 hours with micrometer precision. The diamond wire is just 120 micrometers thick, roughly the width of a human hair, yet it slices solid crystal. Edge-rounding chamfers, each sharp corner, preventing microchips that would become fatal cracks during cell processing. Laser scanning maps thickness across every wafer. Deviations beyond 10 micrometers trigger automatic rejection. Every wafer is inspected for microcracks. A single flaw here means a dead cell at the end of the line. Chemical baths remove sawing damage, preparing atomically smooth silicon for the cell fabrication line. At any given moment, this facility holds over 1 million wafers in various stages of processing, a river of silicon flowing through the factory. Welcome to cell fabrication, where bare wafers become solar cells. First is texturing. Acid etches millions of microscopic pyramids into the surface to trap sunlight. Invisible to the naked eye, these pyramids cut light reflection from 30% to just 8%, dramatically increasing energy capture. Wafers enter a diffusion furnace at 850 degrees, where phosphorus atoms are driven into the silicon surface to create the electrical junction. This phosphorus layer creates the negative side, paired with positive silicon beneath, forming a one-way gate for electrons. The p-n junction is the engine of every solar cell. Sunlight knocks electrons loose. The junction forces them to flow in one direction. Laser edge isolation scribes a precise groove around each wafer, preventing the front and back electrical layers from short-circuiting at the edges. Sheet resistance measurements verify the phosphorus layer is exactly right. Too thin and the cell underperforms, too thick and electrons recombine before collection. Between every major step, wafers pass through chemical cleaning baths, removing surface contaminants that would cripple cell performance. Laser edge isolation scribes a groove around each wafer, preventing the electrical layers from short-circuiting at the edges. Sheet resistance measurements verify the emitter layer. Too thin and the cell underperforms, too thick and losses climb. Between every major step, wafers pass through chemical cleaning baths, removing contaminants measured in atoms per square centimeter. Plasma deposition coats each cell with silicon nitride, an anti-reflective layer just 75 nanometers thick. This gives solar cells their iconic blue color, tuned to absorb maximum sunlight across the visible spectrum. Not just decorative, 96% of incoming light now passes into the cell instead of bouncing away. Screen printing deposits electrical contacts, silver lines, 40 micrometers wide, collecting electrons without blocking sunlight. Each cell receives 100 milligrams of silver, forming a complete electrical highway across the surface. The firing furnace flash heats each cell to 800 degrees for seconds, burning silver through the coating to contact silicon beneath. This step is critical. Too hot and the junction is damaged, too cool and the contacts fail to penetrate. The back surface gets aluminum, bouncing escaped photons back for a second chance at absorption. Selective emitter technology uses lasers to create heavier doping directly beneath the metal contacts, boosting current collection without increasing surface recombination. Infrared imaging catches invisible defects, hot spots that would slowly destroy a cell over years of operation in the field. Selective emitter technology uses lasers to create heavier doping beneath contacts, boosting current collection efficiency. Infrared imaging catches invisible defects, hot spots that would slowly destroy a cell over years of operation. Every single cell is flash tested under simulated sunlight, sorted into bins by efficiency within tenths of a percent. Modern PERC cells routinely achieve 23% efficiency, meaning nearly a quarter of all sunlight hitting the surface converts directly to electricity. Cells are matched by efficiency and color, preventing weak links in the finished panel. Inspectors catch what machines miss, subtle cracks and printing defects, reducing lifespan. Copper ribbons soldered across each bus bar link cells in series, building voltage step by step. Each string contains 6 to 12 cells soldered in sequence, and 6 strings combine to make a complete panel circuit. 60 cells arranged in perfect formation, each one contributing roughly half a volt to the panel's total output of 30 volts. Panel assembly follows a precise sandwich: tempered glass, EVA film, cell matrix, another EVA layer, and protective backsheet. EVA is the glue holding everything together, protecting cells from moisture and stress for 30 years. The laminator heats to 150 degrees under vacuum, melting EVA into a permanent bond. 20 minutes under heat and pressure transforms 5 separate layers into a single sealed unit. Waterproof and impact resistant. Panels cool on racks. EVA needs time to cross-link and reach full adhesion. Laser-precise trimming removes excess material from all 4 edges, preparing a clean surface for the aluminum frame. Silicone sealant creates a weatherproof barrier between frame and glass, designed to withstand decades of UV exposure, rain, and temperature extremes. A finished panel contains 7 distinct layers and over 100 individual components, all engineered to survive 30 years of outdoor exposure. Environmental chambers simulate decades of weather in weeks. Panels endure extreme heat, freezing cold, humidity, and UV radiation to prove long-term durability. Silicone sealant creates a weatherproof barrier between frame and glass, designed to withstand decades of UV and thermal cycling. A finished panel contains 7 layers and over 100 components, all engineered to survive 30 years outdoors. Environmental chambers simulate decades of weather in weeks, extreme heat, freezing cold, and humidity proving long-term durability. The frame channels rainwater from electrical connections and provides mounting points for installation. The junction box is the panel's electrical gateway, housing bypass diodes that protect cells from damage when partially shaded. 3 bypass diodes route current around any shaded cell group, preventing hot spots that could permanently damage the panel. Every panel faces a final exam, a solar simulator flashing calibrated light equivalent to peak sunlight conditions. Panels falling below rated wattage by 3% are pulled, ensuring every unit meets its 25-year guarantee. Electroluminescence imaging reveals invisible microcracks, catching defects that flash testing alone would miss. High voltage testing confirms safe insulation, protecting installers and homeowners from shock hazards. A final clean removes every fingerprint and dust particle, because even minor surface contamination reduces light transmission. Each panel gets corner protectors, shield film, and a serial number tracing it through every step. 30 panels per Pascal, let 40 pallets per truck, enough to power 1,200 homes. From this dock, panels ship across 6 continents, arriving within 10 days of leaving the line. Logistics teams coordinate shipments across ocean freight and overland transport, timing deliveries to match installation schedules worldwide. Distribution centers sort panels by destination. A single facility might ship to 40 countries in a single week. Commercial installations can span entire rooftops, turning wasted space into power plants that slash energy bills by up to 70%. Logistics teams coordinate shipments across ocean freight and overland transport, timing deliveries to installation schedules worldwide. Distribution centers sort panels by destination. A single facility might ship to 40 countries in 1 week. Commercial installations span entire rooftops, turning wasted space into power plants that slash energy bills. At the installation site, teams mount panels in precise arrays, tilted at the optimal angle to capture maximum sunlight throughout the year. A residential system installs in 1 day, 8 hours producing 25 years of clean electricity. Utility-scale solar farms span thousands of acres, each one replacing a coal plant's worth of carbon dioxide every single year. Grid tie inverters convert the panel's direct current into alternating current, synchronized perfectly with the utility grid's frequency and voltage. At end of life, panels enter recycling facilities that recover 95% of materials: glass, silicon, aluminum, and copper, returning to the manufacturing stream. Bifacial panels capture sunlight from both sides. Tracking mounts following the sun's path boost energy output by up to 40% over fixed installations. Floating solar farms are the newest frontier, installed on reservoirs. They generate power while reducing water evaporation by up to 70%. Grid tie inverters convert direct current into alternating current, synchronized perfectly with the utility grid. At end of life, panels enter recycling facilities, recovering 95% of materials: glass, silicon, and copper, returning to the supply chain. Bifacial panels capture light from both sides. Tracking mounts following the sun boost output by up to 40%. Floating solar farms generate power on reservoirs while reducing water evaporation by up to 70%. Sand mine to shipping dock in 2 weeks. Yet, these panels generate clean electricity for 3 decades, 14 days, 400 steps, temperatures from -200 to over 2,500 degrees, all to turn the most common material on Earth into one of humanity's greatest inventions. The solar industry now generates over $200 billion in annual revenue, growing faster than any other energy source in history. Behind every panel, thousands of engineers, technicians, and operators turning science into mass production. What started as sand is now silently converting sunlight to electricity. No moving parts, no fuel, no emissions. The factory runs on solar power. Panels producing panels in an endless clean energy cycle. Panel prices dropped 99% since 1977, from $76 per watt to under 20 cents. Tandem cells combining silicon with perovskite promise efficiencies above 30%. Factories already retooling. Thin film technology promises solar cells flexible enough to wrap around buildings, turning every surface into a potential power source. Building integrated photovoltaics will transform cities themselves into power plants. Facades, windows, and roofing tiles all generating clean electricity. Perovskite solar cells have shattered laboratory records, reaching 33% efficiency in tandem configurations, nearly 50% better than current commercial panels. Thin film technology promises cells flexible enough to wrap around buildings, turning every surface into a power source. Building integrated photovoltaics will transform cities into power plants. Facades and windows all generating electricity. Perovskite cells have shattered records, tandem configurations exceeding 33% efficiency in the laboratory. From a single grain of sand to clean energy for an entire planet. This is how solar panels are made. This factory ships 10 million panels yearly, just one of hundreds powering the solar revolution. If you enjoyed this journey from sand to clean energy, subscribe. We will see you inside the next factory.